Welcome. Today we're going to talk about Fourier type integrals using residues. Okay, so let's talk about, remember that what we have here is integrals of the form. So here if we have like a Fourier transform, the Fourier transform, I mean there's many different alternate versions of it, but they're all of the form this, so that represents the transform. It's a real integral, an integral on the real line of f of x times our complex exponential e to the I omega x dx. Okay, so so of course this exists provided f it falls with certain restrictions on its integrability. So we're going to talk about a special class of f of x functions that residue theory allows explicit answers, explicit computable results. Okay, and so of course what we're talking about is f of x of a rational type of the form p of x over q of x, where both of these, numerator and denominator, are polynomials. Okay, and these polynomials, they have a real coefficients, and another thing is we want q of x should have no real valued zeros. So clearly if q had a real value 0, then there would be a singularity that was actually on the real number line, in which case there would be questions of whether or not the integral would converge. And so we don't want to consider that kind of thing right now. So what we're talking about then again is something of the form this way. And what that means is that, and also that, so what we mean then is that of course we're going to get complex conjugate roots. For q, and that means I can, if I draw out my complex plane here, we're going to have roots like this that all over the plane like so. Okay, and so with these, as we've seen from before, what we can do is of course take an r that's a capital R that's big enough so that we can create a contour integral. The first branch of the contour integral is going to go like that, and then it's going to come around in a semicircle over the top, like so, and it will enclose all the roots in the positive complex plane, or the top half of the complex plane, I should say. And so, of course, we're going to call that contour C. And C is going to be broken into two pieces. I'm going to call it CX, this part that's on the bottom there, and also CR, the radial part that goes over through the complex plane. And of course, what we know from this is that this integral C over the contour C that encloses all of those roots in the top half of the plane of f of z times e to the I omega x dx is going to be equal to 2 pi I times the sum of all the residues of f e to the I omega x, or sorry, z, that should be a z up there, z, where z equals zk for all of those singular points that are in the plane, on the top half of the plane. Okay, and so the goal will then of course be to take r going to infinity and then be able to establish that these residues all these residue values that are accumulated can be attributed just to the the integral along the real line and not to this radial component here as well. So that's the goal. All right, so let's see how we can do this. We need one more assumption. We need to assume that omega is positive. Okay, and for many of our analyses involving Fourier series or Fourier analysis, we can always assume that omega is of one sign, so we can just pick the positive side and make omega positive. Okay, so with that result, we can get a solid answer here. So with that assumption, I should say. Okay, so let's just talk about an example. So let's try this example here of f of x is equal to 1 over x squared plus 1. And of course, so again, our Fourier transform of f is going to be e to the I omega x over x squared plus 1. All right, and clearly we can rewrite this. We can factor the denominator into x plus I and then x minus I. Okay. All right, and so when we draw the complex plane here, we have a I and then a minus I down there. So there's the complex conjugate roots, and we can put our path going around like so. So what we can do, of course, is now that encloses that path, so we'll call that C. And so what we do is we examine f of z e to the I omega z dz and say that's equal to 2 pi I times the residue of f of z e to the I omega z. Okay, so the residue is going to be at I. Right, it's because it's enclosing that one right there. Okay, so let's actually compute what that is. So we can rewrite this function here on the inside. Now, in terms of this, we can rewrite it as e to the I omega z all over z plus I. That corresponds to the singularity in the bottom half of the plane. And so this function, of course, is analytic inside C, and then we have our singularity in the denominator like that, and we know using the residue theorem that what we do is it's 2 pi I times e to the I omega z plus I evaluated at z equals I. That is the value of the residue. And that's because we have a first power, a simple pole. Okay, so let's calculate what that is. That becomes a 2 pi I all over 2I e to the negative omega. Okay, because I times another I makes a negative 1. So those cancel there, and we get a pi e to the negative omega. And that's true provided our capital R is bigger than 1. And because we're going to take R to be big, very big, we can ensure that for every value beyond that, we're always enclosing the singularity. And this contour integral is always going to be the same value, pi times e to the negative omega, for omega greater than 0. And we're going to use this assumption a little bit later to do something. All right, so the question then, of course, is that this contour integral is actually of f of z e to the I omega z dz is actually, we can break it up into two pieces. One is the negative r to r, e to the negative omega I omega x over x squared plus 1 dx, plus integral CR, that's this top half, and that'll be e to the I, sorry, that should be a positive I there, I omega z over z squared plus 1 dz. Okay, and that whole thing provided r, capital R is bigger than 1, we have is equal to pi e to the negative omega. So the goal, of course, is to, as r gets big, we need to analyze analyze this when r goes to infinity and prove it goes to 0. Okay, so and that means then, of course, that as r goes to infinity, it means that this integral here then can be associated with that value, and this contributes nothing because it goes to 0. Okay, and then we have successfully computed, or very nearly successfully computed, the value of this integral, because again, this is the objective, is to catch what this value is. And if this thing here goes to 0, this contour, this radial contour, the semicircle in the top half of the plane, if that goes to 0, then the value that we've accumulated here from this contour integral can be associated with that improper integral. Okay, so let's see if we can do that. And so we're gonna use several tools from complex variables analysis to see if we can analyze this thing. So I'm going to write down what those tools are. Again, what we have is, redraw it in the plane, we have our contour CR up here. It encloses I, goes from R to negative R, and on that whole contour, Z will be equal, the modulus of Z will be equal to R. Okay? All right, and we're going to use two tools. So again, we need to prove that this integral CR e to the I omega Z Z squared plus 1 dz it goes to 0. So the tools we're going to use is that of the integral bound. So, and let me talk about what that is again. So in general, what we have here is if I have some function g of z, and I have a contour C, and I say, suppose that m of r is, sorry, I'm going to redo that, g of z, the modulus of g of z for z that are on our contour, which I'll call CR, is less than or equal to mr, where that is maybe parameterized by our capital R, then, and we've seen this theorem before, that we can take the modulus is going to be equal to mr times the L, which is the arc length of CR. In this case, of course, CR is equal to pi times R because it is a half circle of radius R. Okay, so there we go. That's one of our tools. That's the first tool. The second tool is that of the triangle inequality. And this is in order to find MR right there. We need to be able to find this MR, and so we're going to use that. And so recall, if we have something of the form Z plus A over Z plus B, where A and B are complex numbers and Z is a complex number as well, we can always bound it using the two versions of the triangle inequality. We use the upper bound for the numerator, and we use that lower bound for the denominator, where we take the difference. Okay, all right, so we're going to use that a whole lot in order to find this bound, okay, because recall that, of course, that Z is equal to R, okay, in our particular case. So let's do that. Let's find this bound here, E. So let's oops. So what we have here is we look at the the integrand inside of here, we have e to the I omega z all over z squared plus 1. And we know, I'm just going to leave that numerator alone for right now. Okay, and I'm going to look at the denominator, and we can use the difference bound triangle inequality. Oop. There we go, like that. All right, and of course I know that that is equal to the modulus e to the I omega z all over r squared minus 1. And that's because r is bigger than 1. We can do that. We can take off the absolute values. The next thing we need to do, of course, is, because again, what we're doing is, of course, we're finding that bound on the curve itself. So we're only looking on the curve, in which case we know that z, the modulus of z is equal to capital R. The next thing we need to do is examine this, e to the I omega z, which is e to the I omega x plus I y, which is equal to e to the I omega x times e to the negative omega y. And that, of course, is, we can break that up into two moduli like that. This, of course, because this is a pure imaginary number, is always going to be 1. And recall, of course, up here that y is always greater than or equal to 0. And we also said that omega is greater than 0, in which case this thing right there is always going to be less than or equal to 1. All right, so now we have a nice bound there. We can continue on and state then that we have this integrand here is less than or equal to 1 over r squared minus 1. All right, so let's take this result and finally bound our thing. So again, we wanted to look at we wanted to take this part of this component of our contour integral, and now we have a bound for it. It's 1 over r squared minus 1. And now we have to multiply by the arc length, which was pi r. So what we have here is pi times r to the first power over r squared minus 1. Of course, we know that as r goes to infinity, then this thing goes to 0. In which case, we finally conclude then that the limit r goes to infinity from negative r to r of e to the I omega z, sorry, not z, x over x squared plus 1 dx is equal to, is going to be equal to what we had found from the residue theorem, e to the I negative omega. Okay, all right, so that's good, but we have a little bit more of an issue here because, of course, this is equal to the principal value integral of e to the I omega x, x squared plus 1. So we need to find out, is it equal to the actual, I'm going to put a question mark there, is it equal to the actual improper integral of e to the I omega x, x squared plus 1 dx? And the answer is yes, because of course the e to the I omega x is equal to cosine omega x plus I sine omega x. And so this part right here is even, and this is odd. And that's the imaginary part. But it turns out, of course, that we know that now if I break this integral into two pieces, this principal value integral into two pieces, I get one piece over the reals. I can just write that as an abbreviation of cosine omega x over x squared plus 1 dx. That's the real part, and that has to be associated with the real part on this side. And also, and in addition, then, of course, we have the imaginary part, sine omega x, x squared plus 1 dx. That's going to be equal to, the two halves. Sorry, that has to be from there to there, sine omega x over x squared plus 1 dx, plus 0 to infinity of the positive part of the integral. And what we have here is that this, of course, it converges, and this converges to an equal and opposite sign, in which case they both net out to 0, which explains why that works. So actually, our integral, this integral that we wanted to compute is actually equal to just the cosine part, because of course that is the real valued part, which we have there. But anyway, from this result, we can actually say yes. No longer a question. This is an even function, and so the principal value, the even part of this function, which is equal to the principal value, is going to be equal to pi e to the negative omega. Okay, so that gives us a nice result and shows a good way of computing these integrals of Fourier type. In later videos, we'll talk about how to other theorems that allow us to establish these results a little bit more smoothly, so we don't have to do so much analysis. All right, so thank you very much.